No, literally. Because it's only.
That is, you have to break when you
So
can.
I do.
Things are addressed material more and more every single day. We're sort of improving slowly and steadily. And stuff, you know.
Yes.
So they have like bunch of she's that's 75 is too hard like things. So that sounds pretty hard for me to make
Yeah,
stuff
but
like
I'll switch up wires. How many people are trying, like, it's in the first and last semester. It's gonna be very hot.
Okay, so we're having is there anybody here that takes a bus in and can't get here before 7:50? Like 7:45 start? Okay, how about 7:55?
I can do that.
Oh, yeah.
7:55 is okay?
Sorry, yeah.
Yeah, you can't get it by 7:55?
No, yes, I can. Sorry.
Okay, good. All right, so I'm gonna actually send the email officially to ask you guys to make sure, anybody that wants to extend this, you tell me that proudly, via email, and I
No,
thank you. But my plan is to run these in for an hour from 7:55 till 8:55, and then give you all a grace period during okay? Okay, let me say something about the next homework, because obviously you don't want me doing this while you're trying to take the test. So this will be due a week from Friday. The first one I think is kind of a fun one where we look at SN, particularly in this case, S7 at the beginning. S7 has 7 factorial, 5,040 elements in it. What I want you to do is for every possible order of an element, right? Find me, or tell me how many elements of that order there are. And of course, we should come up with 5,040 all total. Number B, let P be a positive prime integer. How many elements of order P are there in SE? Prime is important here, it makes it easier to count. And a follow-up to that is how many subgroups of order P are there in SP? Number 3, let G be a group. Show that the inner automorphisms of G that was defined in the previous homework set is isomorphic to G mod the center of G. Number 3. This problem is about characteristic. A group is characteristic. It's sort of like a normal subgroup on steroids. It's a stronger kind of condition. We say that H is characteristic in G if D of H is contained in H for every automorphism of G. Show that if H is characteristic in G, then H is normal in G. So anything that's characteristic is normal. Show that if H is characteristic in G, then this means restriction. When you restrict this automorphism of G down to H, this is an automorphism of H. As a follow-up, give an example of a group G that has a normal subgroup that's not characteristic. So characteristic is truly a stronger, than normal. Suppose that H is characteristic in G and suppose H is characteristic in K and K is characteristic in G. Does it follow that H is characteristic in G? Prove this or give a counterexample. Notice this is the same problem I asked you about normality. Let's see what happens here. And number 4, this is kind of a cool classification problem. So once again, classification. Suppose I walk up to you on the street and I give you a group and it's got 2 P elements where P is prime. So that could be 10, it could be 14, it could be 202, any 2 times of prime. Show that one of 2 things happens. This is either isomorphic to Z mod 2Z, or I'm sorry, Z mod 2P if G is abelian, right? And in fact, if it's abelian, it's cyclic. And if it's not, then it has to be dihedral on P. So if you have 2 times an odd prime, there are only 2 groups. One of them is cyclic abelian, the other one is dihedral group. I'll give you a hint to kind of start this one off. You know from Cauchy's theorem, there's a subgroup order P, and it has to be normal, but I think that might help. Okay, Any questions? Yes.
There you do some with for any, n greater than two people, so let's say 3D.
Oh,
At what point does it bring it down? Is it just-
well, I mean, there's lots of directions you can go. If you replace p by any odd integer, this doesn't work anymore. And groups of order three p, yeah, so, yeah, there can be, there are cases where there are groups of order three p where there's only one, right? So for example, 33, well, 3 times 11, there's only one group, there's only the cyclic group. So it's a bit different in that case. Okay, other questions?
So what's that 23.09 mean there?
It means that somebody didn't erase the board last time. Okay. So, last thing that we talked about was I gave you the statement of the second isomorphism theorem, which I will do again. Let H and K and G are subgroups of G, and I know that H is contained in the normalizer of G of K. H then H intersect K is normal in H. And you have the isomorphism HK mod K is isomorphic. Okay. So let me set some things up a little bit and then we'll talk about strata. First of all, we know that HK is a subgroup of G. Since H is in the normalizer. We have HK is so. Right. Okay, so we also know from homework that H intersect K is normal, is a normal subgroup of H. That was one of the homework problems. And now, what do I want to do to pursue strategy? So I want to show this isomorphism. And one thing that I could do is I could get out my heavy lifting and try to construct an isomorphism directly from here. Anybody want to do lamentations about why this might be a pain in the butt?
We don't really have an established isomorphism from one to the other.
Right, and even that, to go from here to here, or if I go from here to here, these are both cosets, right? This is a collection of cosets, so it's this, right? So whatever function I set up, I'm gonna have to prove it's well defined, which, don't really want to
We
do.
need to find a homomorphism first, then we need to show that homomorphism is an isomorphism.
So. What might I do here? I am going to find a function. I want the first isomorphism theorem to do some heavy lifting for me. I want to construct a function from, I'm gonna go in this direction, but I don't want to go from this coset because it's just too annoying, so. Let me first point out. Hey, normal in. Anybody say why that is? Well, let's let X being K. And HK and H. Look at. Look at this conjugate. We need to show that it's in K. Right? Anybody see why that's the case? Well, let's go write this out. This is K inverse, the root of H inverse, X.
In HK.
Good. So H inverse X A1.
Which means that it exists in K.
Everybody okay with it? This chunk in the middle is actually known as K. So.
This in HK.
Everybody okay?
Yeah, I follow.
So. This makes sense. I am going to define a function that I'm going to prove the homomorphism. So we're going to define P from H to HK mod. And the good news is I'm not going to really have to worry about well finals. Let me ask you here. Remember, this is math class. So what is the easiest way that I can take some element of H and make it a coset of HK and K? What's the easiest element of HK that I can associate with H?
Well, H.
For emphasis. The H, an element of H and the element of K together.
Yep, it's all fine.
He's right. This is. This is well defined. Right? Because there's no ambiguity here, right? If this was from H mod, I would have to worry about coset representatives. I don't have to do this. Input H, output this coset. What I have to do with it? Okay. All right, so this is well defined. How about homomorphism? Well, for emphasis, I would write this as. Which is. Okay, so this is a homomorphism. I also claim that this is on. Let me see what is true. First note, I'm gonna make an observation. If H is in H and little k is in K, then these two cosets are exactly the same. It doesn't matter, as long as this little k is in K, it's.
It says K and H instead.
Oh, and the reason is that there's several ways to see this. Notice that this is true if and only if H inverse HK is in K. And this is certainly true because H inverse HK is just K, which is right. So these two cosets, you can think of K as sort of sucking up that K. It doesn't really matter. Right? So if HK is in HK mod K, then HK, okay, that coset is HK, which is T of H. So I've got everything right. Now, I guess my last trick is, what's the curve?
We'll produce the identity element, which is EFK, so it'll have to be K. Or H intersect K.
Which is
H intersect K.
set H and H, such that, what does it mean for this coset to be equal to K? It means that H has to be in K. So this is the set of H and H, such that H is in K, precisely. Now, first isomorphism theorem. H mod kernel is isomorphic to the image. And let's take that apart. H mod kernel of phi, you just figured out it's this thing, is isomorphic to the image of phi, what the map was onto. And there's the same isomorphism. Any questions on I'm sorry? Oh, this right here. So this is the first isomorphism term, right? All we're doing in this last step is put the pieces together. The kernel of phi is H intersect K. And the image of phi is all of HK mod K because we just showed that phi was on to. Okay, other questions?
Without, having the quantity property, is it just, is it always true that it's always, isomorphic to the image?
Yes, that's it. The statement of the first, this is the sort of complete statement of the first isomorphism. If you have phi that goes from G to H, then there's a isomorphism from G mod the kernel of phi onto the image of it.
But why is the image HK, okay, right from that?
Because we proved it was on to. So remember, phi went from H and HK mod K. So you showed it's on to, so that's the image. It's on this. Other questions? Yes.
At one point in the center, you had the, I should have asked it earlier, but it was like, where you have like and you like split it in half, it was like the norm, was that from the normality assumption? Or you didn't know,
Overall, this board,
yeah, like
Yeah.
right in the center, I should have asked earlier. Don't,
yeah,
I'll ask you after class, thanks.
yeah, well, I'm gonna look at the notes, right?
Okay.
Yeah.
I'll show you.
It probably, I think it's probably for the,
That wasn't that.
H is containing the normal.
That, yeah.
Sorry. There, don't worry. Or third isomorphs. There. Okay, this one is an important one because it talks about correspondence. Let N be a normal subgroup of G. Then there is a one-to-one correspondence between subgroups of G containing N there exists a one-to-one correspondence which, if you remember from 3190, what that means, I'm going to talk about two sets. It means there's bijective correspondence between these two sets. And what are those two sets? Between normal, I'll tell you what I put that parentheses in both subgroups. Of G containing N. And normal subgroups of G minor. And I'll show you how the correspondence works.
I'm putting normal in parentheses. I think word.
I'll explain that when I write this down. Well, I'll tell you. You can remove both normals and the statement is correct. So there's a one-to-one correspondence between subgroups of G containing N and subgroups of G mod N. And if this subgroup is normal, then so will the correspondence. So you can either remove both normals or leave both normals. Okay. And here's the of G containing N. more form. Again, it's ignore subgroups. G model. And the correspondence works. I think. Well. And what is more. If H is one of these intermediate groups and H is normal in G, then H mod n is normal in G mod n. So H mod n is a normal subgroup G mod n, and so whenever you got a normal subgroup portion out, oh, this is so sloppy. But anybody want to guess what this turns out to be? Right, you're in an alpha cancel thing, which is super sloppy, but I that happens. Yes.
Should we expect to see the second person?
Expect a strong word, up through today is fair game. Like if I ask you for the state or something like that.
I don't think we should use it on the homework yet, so. It's hard, I look for.
I should use
The first, yes, but not the second, yeah.
I did.
What are you saying? Why is that sloppy? Is it just like a weird? Why do you think it's sloppy?
Because it's just like this is some, algebra one problem from high school. Oh, look, I can cancel the ends. That's a little sloppy. And we're gonna prove that, I need to prove it to make it unsloppy, right? Because if you were in some high school algebra class and say, oh, look, I can cancel the ends. Okay, so let's see why this was true. This is called the correspondence theorem, and this is but let me give you an application of this. How many subgroups of Z contain 12Z? Now, this is I can think of one. Well, of course, Z itself, 12Z, those are the third. The even integers contain this, right? That's another subgroup of Z. But how many are there? And here's the problem with this. Both Z and 12Z are infinite sets. Is it immediately clear that there might be infinitely many, right? Because to go from here to Z, you've got to add infinitely many elements, right? You've got to put in every integer that's not divisible by 12. Right? How do you know there's not infinitely many groups in between there? But there aren't.
Wouldn't it need to be, wouldn't you need to be smaller for both of many, or I say smaller for all the same size, but wouldn't it need to be like 6Z or something else?
Well, and that's the point of correspondence theorem. So if let's call it H. Then H corresponds uniquely to a subgroup of C mod 12C. Or what we call C12. Right? Now, I don't know much, but this is a cyclic group of 12. And its subgroups are cyclic. Of order 1, 2, 3, 4, 6, 12. Right, because for a cyclic group, there's one and only one subgroup for every divisor of the order of the group. Right? And this correspondence, this one right here corresponds to all of Z. This one corresponds to Z12 and so forth and so on. So this actually, this correspondence theorem gives us there are exactly 6 subgroups, including the trivial ones, between 12Z and Z, corresponding to the subgroups of Z mod 12Z. So this is kind of a matching theorem because these two are infinite groups, but now I know there's only finitely many infinite groups in between. So how do we prove this? Well, once again, first isomorphism theorem will come into play.
That 12C is subgroup thing to subgroup.
What's that now?
Is that 12C is a subgroup thing to subgroup?
Yeah, that's right. Okay, I'm showing out the correspondence part. I'm gonna go over details. Suppose in subgroups and n is normal with G. Here's the way the correspondence works. Notice that n is normal in H as well. Because it's normal in G, so it has to be normal in H. So H mod n is a subgroup of G mod n. So the correspondence one way. So is H goes to H mod n. So input subgroup of G between n and subgroup of G that contains n, and this is a subgroup of G mod n. And the correspondence in the other direction, that is from the set of subgroups of G mod n, now suppose I'm going to call this A in G mod n is a subgroup. Now suppose this is just some subgroup. So this is, there exists a set H in G such that A is equal to set of H in for H in. Right, because A is a subgroup of G mod n, so it is a collection of these left cosets, right? It's just some random collection. I know the identity has to be there because A is a subgroup, but I claim this set H is, in fact, a group. well, I know, be more specific, the subgroup of G. uh, Okay, so how would we put that? Well, let's say X, Y, B, H. This means X n and Y n are in A. Right? Because if X and Y are in H, that means these cosets have to look in A. That's how we define H. Well, A is a group. So Xn times Yn inverse, which is Xn Y inverse again, which is X Y inverse. Is in A. Because A has to be true. Well, what does this mean about X Y inverse? If this thing is still an A, what can I say about my label X Y inverse? So H is true. And let me also point out that, of course, everything in N has to be an H. Because if you have an N in N, that thing has to be an A. So H, in fact, is a subgroup P that contains H. So the correspondence I'll call that correspondence phi. Notice it's an easy check that if you start with H, you go to H mod N and then do phi. If you start with H here and go to H mod N, this goes back to H. And if you start with H mod N and go to H, and then do this part of the correspondence, you come back. So compose identity in both directions. So one to one. Okay, there's that part of it. So I have one-to-one correspondence between subgroups of G that contain N and subgroups of G mod N. Okay, what other mounts do I have? Well, now I want to show the normal part. Now, suppose H is normal in G. We claim H mod N is normal in G mod N. This one's fairly easy because let G and B, this goes at here, H and here. If you look at G in inverse, H in, G in, I can simplify this down, taking a couple of steps of liberty here. Is that. Right, and this is in H mod N as H is normal. This conjugate is still H, so that means H mod N is normal in G mod N. So I've got that thing. What about the other direction? What if G mod n, what if H mod n is normal G mod n? I need now to convince myself that H is going to be. So let H be an H, G be an G. And consider this coset here. This is the same thing as G n inverse H n G n. Everybody okay? And because H mod n is normal to G mod n, this is let me write this. So what I have here is G inverse H G is equal to n is equal to H prime. That's what this computation shows. This thing right here has to be a coset of this. Let me get down to brass tacks. This means that inverse right. But that's what it means for these two cosets. The inverse of this times this has to be an n. But here's the rub. N is contained in H. So that means that H prime inverse G inverse HG H. But this is in H, so this implies G inverse G and H. And so H is in H. So now we've shown that normalities, so we've shown that there's a correspondence between subgroups of G that contain N and subgroups of G mod N. We've shown that one is normal, the other is normal in the correspondence. The last thing we have to do is show that last isomorphism. So finally, suppose H is normal. Yeah, we have N subgroups. And we know N is normal G as well. That's a blanket assumption. The last part of the first isomorphism theorem we show. So consider well, let's do the correspondence there. Let's try to do the first isomorphism theorem here. Oh, actually, let's do it this way. G multiplied. No, this way. I could. Better do. Let P go from. Um. Given by. Take a random coset of this thing, so G N. My output's gonna be a coset, what's the easiest thing? Just whatever representatives do it here. Now. What do I need to worry about here? I need to worry about if this is well defined, because I say tomato, you say tomato, they're different representatives. So let's suppose. Since my domain is cosets and I have different representatives, I need to worry about this being well defined. Suppose G1N is equal to G2N. So suppose that we pick different representatives, potentially different representatives of this coset. Then as N is contained in H, well, here, this implies that one A. Right? How do I know this? Because if these two cosets are the same, they certainly have overlap, right? That means in particular that G1 is in this coset, right? So G1 is going to be in this bigger coset because N is contained in H. Right? And since these two cosets have something in common, they have to be equal. Right? Agree with that? So E will prime. It doesn't matter what representative we pick for this, the output will be the same coset. Also note, P is onto. Because an arbitrary element of this over here is in form GH, and it just comes from GN. Right, so everything's covered. What is the kernel map? So it's the GH equals. Well, this is true if and only, what can you say about little g?
Well, it's an H.
So this is the set of HN. So some H is in H. So her phi is equal to H. This is exactly the cosets that come from H. Therefore, first isomorphism G mod N mod kernel P is isomorphism. And this is similar to the way we finished it last time. G mod N, the kernel of phi is H mod N. It's isomorphic to the image P, which is G mod H. Okay, any questions on that? questions? All right, don't forget, this is a perfect place to end, I guess, we'll start on the spectrum groups after the exam. Well, we'll start more deeply on spectrum, there are nothing to do with there. You, this evening, 6 p.m. here. The exam. Friday. Again. Well. 7:55 a.m. Question mark on some email in the at 8:55. I'm ready to get it.
Will the review be built for it?
Yes, technology permitting.
Okay.
Right. I will sit down and email to see if we can focus by that. I will call as far as office hours for Friday morning. I'll probably try to get here, before 4 o'clock. So, you know, when we come back, I'll probably leave my office about 4 o'clock. Okay. See you all. This evening.